Hello and welcome. In this video, we'll see what rings mean. Not these rings. Welcome back. It's been more than a month since my last upload. In the last video, we saw what group is under addition modulo 12. It basically worked like a clock. Let's revise what we saw and build on it. Let's get started. So it basically works like a clock where identity was 12. So basically 12 is equal to 0. So that when you add 3 hours to 12, you go 3 steps ahead, 1, 2 and 3, and you go up to 3. So 12 plus 3 basically works like 0 plus 3, which is equal to 3. This is all happening in modulo 12. Similarly, when you perform 11 plus 3, you go 3 steps from 11, 1, 2 and 3, and you get the answer 2, which is under modulo 12. In this case, negative 1 will work as 0 minus 1, but 0 is 12, so 12 minus 1 would be 11. So minus 1 mod 12 is actually 11. 11 can be written as minus 1. 1 can be written as 13. And so on. In the same way, we can define multiplication. Let me get rid of all this. When we think of multiplication and perform 2 multiplied by 3, let's say, it will be 6. And modulo 12 also this becomes 6. Let's think of a harder example. What is 2 multiplied by 6? 2 multiplied by 6 is 12. But 12 in here is 0. So this becomes 0 mod 12. When we think of integers, the product of any two non-zero integers is always non-zero. But here two non-negative integers is giving the product as 0. This can happen in modular arithmetic. That's why these clocks or these groups are special. Similarly, all the multiplications will work. Let's see an easier example. This clock is exactly the same, except here there are only 6 digits. And here our identity is 6. So 6 is basically equal to 0. This clock only has 6 hours. This group is called as Z6 or group of integers modulo 6, which will contain integers from 0 up to 5. 6 will again be 0, 7 will be 1, 8 will be 2 and so on. Let's see multiplications in this. As we already saw, 2 multiplied by 3 is 6, but 6 modulo 6 is 0 because 6 is 0. Now here again, product of two non-negative integers is coming out to be 0, which in regular multiplication is not possible. Just for fun, let's make a multiplication table. So when we say 0 multiplied by 0, it will mean 0. Similarly, 0 times 1 will be 0, or 2 times 2 will be 4, and so on. We have to make this table complete. So when I say 2 multiplied by 4, that is 8. 2 multiplied by 4 is 8. With modulo 6, this 8 becomes 2. So 2 times 4 is again 2. and in the similar way we fill the whole table. So this is the multiplication table. As we can see, 5 times 5 becomes 25 and 25 modulo 6 is 1. From this multiplication table, it is clear that the product of any two members of Z6 is in Z6. So for any A and B in Z6, we have A multiplied by B belonging to Z6. Of course, this multiplication is modulo 6, so we can write a small suffix 6 here. Now if we take this multiplication to be our main operation, what happens? Is Z6 a group under multiplication? We already know that Z6 has the members 0, 1, 2, 3, 4 and 5, where 0 is the additive identity. What about the multiplicative identity? Well, the multiplicative identity is always 1. How about the inverses? Can we have inverses for all elements? As I said, 5 multiplied by 5 is 1. So 5 must be an inverse since it gives out multiplicative identity when we have a product with 5. So 5 has an inverse 5. 1 has an inverse 1. Since 1 multiplied by 1 is also 1. How about other elements? 2 does not have a multiplicative inverse. Since 2 multiplied by any number from this multiplication table we can see is not 1. Similar is the case with 3 and 4. Obviously this is also case with 0. 0 never has a multiplicative identity. So no, Z6 is not a group. So in spite of having all three properties satisfied of closure, associativity and existence of identity, Z6 does not make it as a group. But for such structures, we have a term called as a ring. The official definition of rings is that a structure R with two operations plus and dot representing multiplication is a ring if these four properties are satisfied. R plus should be a commutative group, not just a group but commutative group. Second, if R is closed under multiplication, that is a dot. Third, dot is associative, that the products are associative and we can change the parentheses for the order of multiplication. Fourth is that dot should be distributive over plus. Now this might be a little confusing to hear, but it just means that for any three members of R, A dot B plus C will mean A dot B plus A dot C. And similarly, for the second option, A plus B dot C, from the right hand side if we multiply, we get A dot C plus B dot C. We have seen these properties while working with integers and real numbers as well. After watching these properties, we can easily say that Z6 is a ring, since Z6 with addition modulo 6 is a commutative group. It is closed under multiplication modulo 6. It follows associativity for multiplication modulo 6. And multiplication is distributive over the addition. We have one extra property of existence of identity. This is our bonus. With all these properties, we can easily say that Z6 is a ring. Of course, we have other examples also. We know that integers under usual addition and multiplication is a ring. Similarly, the pattern follows for rationals, reals, and complex numbers. Apart from these, what we have seen here is that Z6 is a ring. Similarly, we can prove that Z12 is also a ring. In fact, integers under addition and multiplication modulo any positive integer n is a ring. If we consider the set of polynomials in X with real coefficients, that also becomes a ring. If we consider 2 by 2 matrices with real entries, that's also a ring. As we saw, Z6 has the identity 1. That's why it is called as a ring with unity. As we have seen, the rings have multiplication and addition as its primary operations. But with inverses, but with additive inverses, negativity also comes. So we have three operations in rings: plus, minus, and multiplication. Along with these three operations, if division is also present, we call it a division ring. If dot is commutative, we call it as a commutative ring. If a division ring is commutative, we call it a field. We will consider this topic in our next video. I hope you understood the concepts considered in this video. In next video, we'll learn another structure called as a field. Till then, give a thumbs up if you like this video, share with your friends, comment down below with your opinions, and please consider subscribing if you like this channel. Thanks for watching till the end. Bye.